Hello, my name is Wook Kwon from Yonsei University in Korea. Today I will present about lithium metal anode dendrite growth prediction via neural networks during repeated charging and discharging cycles. So here's my content. So the lithium-ion batteries use lithium metal as anode and cathode, with lithium-ion moving between the cathode and anode internally. As a result, the electrons move externally through circuits powering our devices. These lithium-ion batteries have growing market size due to their high energy capacity based on electrochemical reactions. Also, they have long life cycle, which is high advantage on our environment. However, they have safety issues such as fire hazard due to dendrite growth problem. Now let's delve into a critical challenge associated with lithium-ion batteries, which is the dendrite growth. Dendrites are tiny needle-like structures that can form on the surface of the battery's electrodes, particularly the negative electrodes or anode. These protrusions are composed of solid lithium metal and emerge during the battery's activation and charging cycles. These electrosurface protrusions can significantly impact battery performance and safety. Here's a closer look at the dendrite growing process. Electrode surface protrusions form during activation and deposit on the flat electrode surface. One of the key factors contributing to dendrite growth is the uneven distribution of lithium ion on the negative electric surface, particularly during charging. Dendrite crystals of solid lithium can extend and penetrate the separator. Okay, it can penetrate the separator, potentially causing damage and compromising the battery's integrity. It's crucial to note that the dendrite growth problem poses a fire hazard, making it a paramount concern in the design and operation of the lithium-ion batteries. So understanding and mitigating dendrite growth is vital to enhance the safety and performance of these energy storage systems. In the subsequent sections of this presentation, I'll explore strategies to address the challenges. So I proposed the two methods to address the dendrite growth problem. The one is the molecular dynamic simulation, and one is employing the neural network. So this is the MD simulation, and the other one is the neural network training. The molecular dynamic simulation is one of the primary methods that can simulate chemical reactions and movements of lithium-ion in battery system. It has good interpretability and domain expandability, such as from lithium-ion batteries to lithium-sulfur batteries. However, it requires large computational time. So on the other hand, the neural network has higher computational efficiency once the training is done. However, as it requires training data set without the MD simulations, it cannot expand domain by itself. Basically, we need the data from MD simulations. Our final goal of this research is to develop a lithium-sulfur battery prediction protocol, considering entire battery life cycle and the whole battery system. To do so, both methods should be employed intensively. But in this presentation, I will focus on the neural network training strategy. The MD simulation part will be discussed by the subsequent presentation. So in this research, the neural network is used to predict the next time step state of the lithium-ion battery. Basically, the input of the neural network would be the atomic position and charge of the current time step, and the output of the neural network is the next time steps information of atomic position and charge. During repeated cycling, the external potential applied to the cathodes and anodes is reversed, creating a discontinuity in the temporal domain of the MD simulation. Due to the discontinuity of the applied voltage, it is extremely difficult to train the neural network, relying only on the training data set. So to address this issue, we embedded condition vectors. So basically, we embedded whether the battery is in charging or discharging cycle. And I also embedded the time step, the current time step. So, and our baseline model is the conditional generative adversarial network. This model employs the discriminator, and the generator creates the fake data, which is the predicted data, and the discriminator compares whether the produced data is fake or not between the real data, and if the discriminates it well, it means the generator has the poor performance. If the result can be worked adversarially to the network, we can improve the performance of the generator. So basically, we are training the generator to fool the discriminator. In that way, the performance can be improved. So the whole process is called the single-step prediction. Basically, we're predicting the next time step. And by feeding the output into the input again, we can predict further and further by iterating the entire prediction protocol. So this is the my simulation domain. The training data set is generated with MD simulation, which is already published in our lab on MPJ computational materials. The simulation domain is as follows. The cathode and anode is composed of lithium BCC lattice, and the electrolyte is composed of 1.0 mole per liter ethylene carbonate. The time step is 0.25 femtosecond, and temperature is 300 Kelvin. The voltage is 10 volt, which is periodically reversed during charging and discharging cycles. And the total data set was 10,000. And among them, I used 7,000 as the training data set and 3,000 as the testing data set. And we used RTX A6000 as to train the neural network. So this is the single-step prediction result. Basically here, we checked whether embedding condition works properly or not. If you look at this graph, we can see that the neural network performance maintains same accuracy over the charging cycle and discharging cycle, which means that our neural network model can maintain the accuracy with the different conditions. The average error was 3.43%, and this is my qualitative plot. Okay, this is the multi-step prediction result. Due to the error propagation inherited in single-step prediction, the error increases during the charging cycle. Okay, we started from the beginning of the charging cycle, and as before I mentioned, the error inherited in single-step prediction propagates further and further. But we observed that the error converges to approximately 10%, which shows that condition constraints can guarantee certain amount of accuracy even with the error propagation. The conditioning constraints were whether it is in charging state or not, and its current time steps. If you see the video, the top one is the prediction and bottom one is the target produced by the MD simulation. As you can see, the charge distribution of the predicted results fit well with the target. Here, charge below than 0.1 can be considered as lithium metal anode, including dendrite. Therefore, predicting charge distribution well means that we are predicting the dendrite growth properly. Okay. So for the specific time steps during 20th cycle to 21st cycle, the error range of charge distribution was only 2 to 4%, and the error range of atomic position was only 2 to 3%. The total computation time is 43,000 faster than compared to the MD simulation. So basically, our neural network model only took 1 minute, while MD simulation took 43,000 minutes. So for conclusion, by overcoming the limitations of existing computation studies, prediction protocol can be built that could analyze the atomic charge distribution and atomic position within the repeated charging and discharging cycles. And by utilizing conditional GAN, we proved that the neural network model can predict the sequential state of lithium-ion batteries even in different charging and discharging conditions. And the prediction prediction of our model is 96.54% of accuracy for single step and 90.47% for multi-step. And the total computational time improved 43,000 times. The prediction protocol offers quantitative characterization and real-time visualization of ion behavior during repeated charging and discharging cycles. The rapid predictive capability plays a crucial role in preventing safety concerns like dendrite growth. Through the prediction of lithium-ion battery internal states, the protocol greatly expedites the advancement of innovative battery formulations and designs. And for the future work, I am trying to expand the prediction domain. In this case, what I'm trying to do is expanding the prediction domain. Now the prediction domain is only for the 10 volt. I'm trying to expand it to 6 volt to 12 volt. And also to improve the accuracy of my prediction model, I am planning to embed some information such as momentum conservation and charge conservation at the loss function level, to improve the physical consistency of the output result. So, okay, thank you for listening.
Thank you for a very, very clear and nice talk. So the floor is open for questions. Any questions from the audience? I may start first. So in your simulation, right, it wasn't clear to me whether you could actually simulate the formation of the dendrites.
Yes.
So can you go back to one of the pictures of your MD simulation? Sorry, not your MD, your simulation, to show us, maybe to point to me where the dendrites actually are. So if you go maybe towards the end of your talk. Okay.
Okay.
No, keep going. Yeah, sorry, here, yeah. So, for example, yeah, where it's like can I, you see some layer of lithium, right? So is that the dendrite?
At this point, it is not the dendrite.
Not yet. Okay.
Not yet.
Right.
Here, basically, we can consider charge below than 0.1 can be considered as the anode. So if you can see here, maybe I can show you. Here, this is the contour plot. Okay, this is the contour plot of charge less than 0.1. Okay. As you can see, for the 6 volt, the dendrite growth problem is not a big issue here. Yep. However, as the potential increases, you can see that the dendrite growth is more active. Yes, so this is the plot of the, this is the contour plot. So you can check the shape of dendrite here.
Yeah. Excellent, yeah. Questions? Yes, there's one question there.
Thank you. I didn't quite understand how you did your training. So did you run a long MD simulation and use snapshots from that or configurations from that long MD simulation to do your training for the neural network?
Can you speak it again? Because I couldn't hear you.
In terms of the training of your neural network, did you run a long MD simulation and take configurations from that MD simulation to use for training?
That is right. We ran the long MD simulation, and we took the entire data set and configuration.
How long was that?
How long? It was about 1 month, 43,000 minutes.
No, the actual
training time.
Training time.
Training time was two days.
Not the training time. Sorry, the length of how many nanoseconds or microseconds did you run?
Typically, it's nanoseconds, right?
Nanoseconds.
I need to.
Yeah, that's okay. I was just curious.
So it's basically 1 time step is 0.25 femtoseconds, and each cycle has 250 time steps, and we ran 40 cycles. So maybe we can calculate from there. So the total physical time, I forgot the total physical time. Sorry.
Do rapid calculation in the head.
Okay, maybe I'll talk to you later more about it.
Thank you.